Okay. So, okay, let's start. It's my big pleasure to introduce Claudia Stadlmayr from Munich. And Claudia will speak weak Pezzo surfaces with global vector fields. And I'm very happy to introduce her. Okay.
Okay, thank you. First of all, I would like to thank the organizers for giving me the great opportunity to give a talk at ZAC Marathon. My talk will be about weekday Pezzo surfaces with global vector fields, which is a joint project with Gebhard Martin, in which we gave a complete classification of weekday Pezzo surfaces with global vector fields over an algebraically closed field of arbitrary characteristic. And in this talk, I'm going to explain to you the methods of our classification, first abstractly, and then in an example where we already encounter exciting phenomena. After that, in the end of my talk, I'm going to show you the whole classification tables and point out some cases with interesting features. But before we start with all of this, let me motivate in an introduction why this question is interesting at all and how it fits into a bigger context. So weekday Pezzo surfaces, from the title of my talk, are examples of rational surfaces. And a quite general question you can ask about a rational surface is, what is its automorphism group? So let for the introduction X be a smooth, projective, rational surface. Then we want to know, what is its group of automorphisms out X? In this generality, this question is not so easy to answer, since our automorphism group out X is contained as a subgroup in the plane Cremona group by rational automorphisms of P2 and or by rational isomorphisms of P2. And one problem for determining the automorphism group of X is that the plane Cremona group is quite big, not even finitely generated, and complicated. So it does not give that many restrictions on out X. The second problem we're facing is that in general, it's not so easy to determine the image of this inclusion. Also taking into account that this I is not even defined canonically, since it depends on the choice of a birational isomorphism between X and P2. So instead of answering this difficult question 1, we want to replace it by an easier question. And for that, we observe that out X is not only a group, but it is the k-rational points of the automorphism scheme of X. So, but out X is not only a group, but out X is the k-valued points of the automorphism scheme of X, which I denote by out lower X. For out X, the automorphism scheme of X. So by a result of Grothendieck for projective varieties, the automorphism functor is representable by a scheme which we call out X, and this scheme is locally of finite type. We will need that later. Okay, and this observation leads us now to the easier question 2, namely, what is the automorphism scheme of X, or much easier, what is the connected component of the identity of the automorphism scheme of X? For this, let me first of all recall that the tangent space at the identity of the automorphism scheme of X, or its connected component of the identity, are the global vector fields of X. This also explains the title of my talk, because having global vector fields is equivalent to out X0 being non-trivial. Okay, the key tool for dealing with
Sorry, is it correct in finite characteristic too?
Yes.
Okay.
So this thing here is always correct. Okay, and then the key tool for answering this easier question 2 is Bloorshaft's lemma, which I'm going to explain to you now. Is it also okay if I share the screen like that, or is it too small for you to read?
Yeah, that looks too small.
Okay, then I do it again like that. Okay, so for Bloorshaft's lemma, let f from y to x be a morphism of proper schemes over our ground field K, such that the push forward of the structure sheaf of y is the structure sheaf of x. Then Bloorshaft's lemma tells us, first bullet point, that f induces a homomorphism of group schemes, which I denote by f lower star, from the connected automorphism scheme of y to the connected automorphism scheme of x. So by this f lower star, I don't mean any push forward or something like that. It just denotes that the action of out y0 on y descends uniquely to an action of out y0 on x. And then the second bullet point, if f is not only birational, is not only proper, but additionally birational, then we can say even more. So if additionally f is birational, then this f lower star is a closed immersion. So I didn't tell you how to prove this first point, but I can tell you something about the proof of the second one. So since the image of a morphism of group schemes of finite type is always closed, it is sufficient to check that the kernel of f lower star is trivial. You check that on s-valued points for s some k screen. So you take an automorphism of y times s that induces identity on x times s, and then our automorphism of y times s already has to be trivial since y and x are birational by assumption. Okay, and this second point now raises the natural question, what is the image of out y0 in out x0? And luckily, in this easier setup of question 2, we can describe the image in some simple cases. For example, if f is the blow-up of a point on a smooth surface. And this is the content of the next fact. So fact, due to Neumann, if x is a smooth projective surface, we don't even need rationality here, and f is the blow-up of a point P in X. The blow-up in a closed point in X. Then we can determine precisely what f lower star out y0 is. Namely, it is the connected component of the stabilizer subscheme of our point P in out x0. Okay, and I won't write down maybe before that, I can tell you that in the course of my talk, I will omit this f lower star sometimes, or actually always after this first slide, when I want to consider out y0 as a closed subgroup scheme of out x0. So we omit that from now on. And now I won't write down a rigorous proof of this fact, but I can tell you the idea of proof for those two inclusions which we have to show. So,
excuse me, did you explain what is f low star or not?
Well, it's, I think I explained it a little bit. So if you have the action of out y0 on y, then this action by Bloorshaft's lemma, which I didn't tell you why this is true, descends uniquely to an action on x. And this is the induced homomorphism of groups.
I see. Okay, so it's really just composition of automorphism with f. No, not quite. So you take f inverse, then automorphism, and then f. So you conjugate by f somehow, right? Okay, okay.
But you need that.
That it would work, right?
And 2 has to be f linear as well.
Sorry? What?
So you have an automorphism So you have out y0 acting on y, and this descends uniquely to an action on x, such that your diagram commutes where you have
Okay.
f from x to y, from y to x.
Okay. Mm-hmm.
Okay, so
Then,
yes.
Claudia, sorry, this condition on the push forward of the structure sheaf, does it always hold for birational morphisms?
Mm,
This condition always holds for birational morphism.
I'm
Yes,
not so sure.
yes. For proper birational, it's okay.
Ah, okay.
Okay.
So in this second point, this additionally, yeah, so if you're a proper birational, then this always holds. Yeah, thank you. Okay, yes, I wanted to explain to you why those two inclusions are true. So for this inclusion, you have to check that, or one can show that the action of the stabilizer subscheme of our blown up point on the surface lifts to the blow up at this point by exploiting several times that blow up commutes with flat base change. That's quite an easy proof to write down, but I won't do it here in the talk. The other inclusion, this one, is a little bit more difficult. So for this, we have to show that f lower star out y0 fixes our blown up point P. And this is precisely the case when out y0 preserves the exceptional locus of our blow up. But that is true because the exceptional locus is rigid and our operating scheme out y0 is connected. So E is preserved, the exceptional locus, and therefore our point is fixed and we get this containment. Okay. Now I told you that question 2 becomes, or question 2 is easier than question 1 because of Bloorshaft's lemma. On the next slide, let's see how we can apply Bloorshaft's lemma to our situation. For this, we consider a minimal model of X. So if f from X to Y is a minimal model, then by Bloorshaft's lemma, since this is birational, we know that out x0 is a closed subgroup scheme of out y0. You see, I'm already omitting this f lower star here. And so why does this now solve the problems of question 1? Let's go to the slide above and have a look at what those two problems were. The first problem was that our group in question is contained in something big and complicated. The second problem was that it was hard to determine the image of this I. How are these problems solved in question 2 now? So for question 2, we have this containing subgroup scheme out y0, and this is very easy because we know what the minimal models of a rational surface are, namely they are of a smooth projective rational surface are, namely they are P2, P1 times P1, or one of the Hirzebruch surfaces Fn with n greater or equal to 2. And what happens to problem 2 for problem B for question 2, namely that it was difficult to determine the image of I. That's also dealt with quite easily in our setting now because out x0 can be determined explicitly as iterated stabilizers by the fact we've seen on the previous slide, because f is just a sequence of blowups in points, and then we just intersect the stabilizer subgroup schemes of the points we've blown up and take their connected components by this fact due to Neumann. Okay, so those problems are solved in question 2. And next I want to show you in an example how powerful this approach to question 2 with Bloorshaft's lemma actually is. For this, we consider the blowup of P2 in 1, 2, 3, and 4 points in general position. Up to automorphisms of P2, we can assume that these 1, 2, 3, and 4 points look like this. 1, 0, 0, 2 points on a line, 3 points, 3 points like this, and 4 points with no 3 of them on a line. Then using the fact from the previous slide, we can compute also the connected automorphism schemes by computing the stabilizer subschemes of those points we want to blow up and taking the connected component. Maybe at this point I have to explain this shorthand notation I'm using. So by this shorthand notation, I mean that I denote the R-valued points of out x0 where R is a local K algebra. I will use this shorthand notation for the rest of my talk, but I think it is clear what I mean by that. Okay, so Out x0 can be computed as the stabilizer of this point, and then we take the connected component. This point is stabilized if our first column looks like this. For those 2 points being stabilized, we need the first column like this and the second column like this. For the third column, we see that only diagonal matrices preserve all those or fix all those 3 points. And on the fourth column of our table, we see that we have no vector fields at all if we want to fix those 4 points. And since I will use one of them later in my talk, I'm going to give you the configurations of -1 curves on these surfaces. So here in the first case, we just have the exceptional divisor of our blow up in this 1 point. Here we have our 2 exceptional curves, and this -1 curve, which is the strict transform of the line z equal to 0 through those 2 points. And this becomes a -1 curve since we've blown up 2 times on this line. And here you see in yellow the exceptional divisors of the blown up points, and in normal black lines, the lines between those points in P2. Okay, now it may seem in this example like we've just randomly blown up some points in P2, but in fact it turns out that the first 3 columns of this table, together with P2 and P1 times P1, are actually all strong del Pezzo surfaces with global vector fields. Since every other del Pezzo surface is a blow-up of the fourth column, and we've seen that in the fourth column we already don't have any vector fields anymore. So these 3 columns are all strong del Pezzo surfaces with global vector fields, together with P1 times P1 and P2.
And what do you mean by a strong del Pezzo surface?
I just say strong del Pezzo surface because later we're going to consider weak del Pezzo surfaces. So strong del Pezzo surfaces are just the normal ones where -kx is ample, whereas weak del Pezzo surfaces are the ones where -kx is just big enough. Okay, now seen in this example that if we have strong or usual del Pezzo surfaces and we want to classify those with global vector fields, then this is just an easy exercise. So now let's have a look at the next simplest question about weak del Pezzo surfaces. For this, let me first recall their definition and compare it to the definition of strong or usual del Pezzo surfaces. So a weak or honest del Pezzo surface this has to be defined, is a smooth projective surface, we call it X, with anticanonical sheaf ample, if we're speaking of honest del Pezzo surfaces, or just big and nef for weak del Pezzo surfaces. And we call the degree of X, or what we call degree of X, is the self-intersection of the canonical sheaf Kx. Okay, I'm sure you all heard of this definition. I want to give you a more explicit definition that is equivalent to this one, namely X is either P1 times P1 for an honest del Pezzo surface, or for weak del Pezzo surfaces, it can also be the second Hirzebruch surface, F2, or a blow-up of P2 in at most 8 points in almost general position for weak del Pezzo surfaces and general position for del Pezzo surfaces. General position. Okay, being in general position means that no 3 points lie on a line, no 6 points on a conic, and no 8 points on a singular cubic, with one of them being the singular point. You can check that this lengthy definition in our setting is the same as at most -1 curves are allowed on X.
You mean F0, not F2?
No, I mean F2, the second Hirzebruch surface.
This has -2 curve.
Yes, exactly. And on a weekday Pezzo surface, -2 curves are allowed. On a normal day Pezzo surface, only -1 curves are allowed. But the condition for those blown up points being in almost general position is that at most -2 curves are allowed. And also F2 has a -2 curve, and that's allowed.
But minus canonical class is not ample.
Okay, maybe the writing of my definition was not so clear. So by this definition, I mean,
yeah.
Sorry?
Yeah, big enough.
Yeah, genau, it's big enough. So I mean, a weekday Pezzo surface is one where minus.
Okay. Okay, it's both definitions.
A Pezzo surface is the one where -k is ample.
Okay.
Maybe I could have highlighted it a little bit. Weekday Pezzo surface, big enough. Yeah, okay. Okay, so we know that general position means -1 curves are allowed. Almost general position means -2 curves are allowed. Now I want to give you another reason why question 2 is interesting for weekday Pezzo surfaces, namely that for these surfaces, an answer to question 2 already yields a partial answer to question 1. More precisely, this is the content of the following lemma. So lemma for a weekday Pezzo surface X, let X be a weekday Pezzo surface. Here, weak is not in brackets, so I really mean weak. Then out x0 having positive dimension, greater or equal 1, I mean, is equivalent to X having infinitely many automorphisms. So the K rational points of the automorphism scheme are infinitely many. And as I told you before, the tangent space of out x0 at the identity are the global vector fields of X. So if out x0 is non-trivial, then there are global vector fields. So we also have this implication that if the dimension is positive, H0xtx is non-trivial. This is always true, whereas the reverse implication does not necessarily hold in characteristic P. We will see in the end of my talk some examples where it doesn't hold, but it holds in characteristic 0.
Sorry, I thought that in characteristic 0 it's true for any X. Not correct?
So what do you mean by for any X?
I mean, if dimension, I mean, the statement that for not for weak del Pezzo, just for any smooth project.
Yes. Yeah, exactly. So that's maybe I can already tell you the proof of this one. That's basically Cartier's theorem, which tells us that every group scheme locally of finite type over a field of characteristic 0 is smooth, and therefore it has positive dimension if its tangent space has positive dimension. So you're right, that holds for every group scheme locally of finite type over a characteristic 0 field.
Okay.
Okay, and let me now sketch to you the proof of this lemma.
Sorry, so your point is that for finite characteristic, it's not correct.
Yes, exactly. For finite characteristic, this implication is not correct because there can be weekday Pezzo surfaces, which we're going to see in my last slide of this talk, which have global vector fields, but whose connected automorphism group is finite. So that can occur, and you're going to see an example of that. Okay, so let's have a look at the proof of this implication. This is always true, so we don't even need weekday Pezzo surfaces particularly. So if by assumption we start with the left-hand side, the dimension of out x0 is positive, then since we're working over an algebraically closed field, the K rational points are dense, and therefore there are infinitely many of them. So out x0k are infinitely many K rational points. And on the other hand, we know that out x0 is just one connected component of our automorphism scheme X. So the K rational points of out x0 are at most as many as the ones of out X. Okay, and that proves this implication. Now let's have a look at the reverse implication, for which we really need that we're working with a weakday Pezzo surface. Because we want to consider the following morphism, induced by minus nkx for some n big enough, from x to some pn. I denote its image by x a can, which is the anti-canonical model of x. This morphism will be called phi, and it's birational in some big Pn for some n big enough, small n and big N. Okay, now we have that out x acts on its canonical sheaf kx, so it also acts on minus nkx. This out x action on minus nkx induces an action on the global sections of minus nkx, so it induces an action of out x on Pn. And this action restricts to our given action of out x on x. So this is what we mean when we say minus nkx is canonically out x linearized. So then, since minus nkx is canonically out x linearized, it's difficult to pronounce. We get a map or a morphism of group scheme from out x to the automorphism scheme of Pn, which is PGLM plus 1. And this is not only some morphism, it is in fact a closed immersion. And this is true because phi, our morphism to the anti-canonical model, is birational. So the argument for injectivity here is the same as the one I sketched in the second bullet point of Bloorshaft's lemma, because X and X anti-canonical model are birational to one another. And closeness can also be easily checked, but I don't want to do this in the talk here. And now at this point, we can exploit that PGLM plus 1 is of finite type. Therefore, also out X is of finite type. And since a scheme of finite type over a field has finitely many connected components, also out X has finitely many connected components. Out X has finitely many connected components. But now we know by assumption on the right-hand side that out X has infinitely many k-rational points. We know that there are finitely many connected components. So each connected component, since we're dealing with group schemes, has to have infinitely many points. So also k-rational points. So also out X0 has infinitely many k-rational points. And therefore, its dimension is positive. Okay, and this,
excuse me, the field is algebraically closed?
Yes, exactly.
Okay.
Mm-hmm. And this finishes the proof of this equivalence. I already told you why this is true, and we already discussed that this implication is Cartier's theorem. Or not really is Cartier's theorem, but follows from Cartier's theorem. Okay. So we have proven now this lemma. In our project with Gebhard Martin, we gave a classification of all weakday Pezzo surfaces with global vector fields in all characteristics. And independently, Ivan Cheltsov and Yuri Prokhorov classified all weakday Pezzo surfaces with infinite automorphism group in characteristic 0. And by this above lemma, we see that those two classifications coincide in characteristic 0. Let me now show to you the main theorem. So it was this joint project with Gebhard Martin, and Ivan Cheltsov and Yuri Prokhorov classified all weakday Pezzo surfaces with infinite automorphism group in characteristic 0. And there are, in characteristic, different from 2 and 3, 53 families of weakday Pezzo surfaces with global vector fields. In characteristic 3, there are even more, 61. And in characteristic 2, there are even more than that, 75 such families. And moreover, the approach using Bloorshaft's lemma allowed us not only to determine whether or not the space of global vector fields is trivial or not, but we can actually even compute out x0 explicitly. So explicit description of out x0. Of course, this depends on the chosen realization of x as a blow-up of P2. And we could determine the configurations of -2 and -1 curves on x explicitly. Later, you're going to see an example and all the classification tables where you see all the automorphism groups and all the curve configurations. And now at this point, you might have wondered why there are more families in small characteristics than there are in big characteristics. This has basically two reasons. The first one is that if we fix a configuration of -1 and -2 curves, sometimes there are more weak-Del Pezzo surfaces with this precise configuration in characteristic 2 and 3 than there are in characteristic 0. Let me give an example to you for that. So in characteristic 0, there is only one weak-Del Pezzo surface of degree 3 with an E6 configuration of -2 curves, whereas in characteristic 2, there are 2 such surfaces, and in characteristic 3 as well. And the second reason for there being more families in small characteristics than in big characteristics is that, as I mentioned before, in positive characteristic, the automorphism scheme can be non-reduced. So this is what I meant when I said this implication does not hold in characteristic P necessarily, because there can be non-reduced finite automorphism schemes. So it can be non-reduced. And of course, since we calculated explicitly all out x0s, we can just check in each case whether it is reduced or not. And by doing so, we see that this non-reducedness phenomenon only occurs in characteristic 2 and 3, and also there only in certain small degrees. And this is the content of the next corollary. So if out x0...
I didn't catch, what was the first reason?
The first reason was that for the same configuration of -1 and -2 curves, there can be more weak-Del Pezzo surfaces in small characteristics than there are in characteristic 0.
Okay.
And we're going to see in the table in the end precisely this phenomenon. And I'm going to come back to those two reasons. Okay, so if out x0 is non-reduced, then we're in characteristic 3 and degree smaller or equal 3, or we're in characteristic 2 and degree smaller or equal 4. And now in the last 15 minutes of my talk, or even a few minutes more, as I promised in the beginning, I will explain to you how the proof of our classification works in an explicit example. Okay, let's start with the example. Well, but actually, before we start with the actual example, let me recall an easier example which we did before. Namely, let's consider P2. And we know that its automorphism scheme is PGL3. We want to blow up 2 points on P2, 1, 0, 0, and 0, 1, 0. You've already seen this example before. Then by Bloorshaft's lemma, we can compute the connected automorphism scheme of the blow-up of those 2 points as the intersection of the 2 connected stabilizer subgroup schemes. And we see this point is fixed if the first column looks like this. This point is fixed if the first column, the second column looks like this. And you've already seen before that the configuration of -2 and -1 curves in this step. So here we have our 2 exceptional divisors. Okay, and now what I really want to do in this example is I want to consider this recalled example as step 0. And in each of the following steps, I want to blow up some more closed points on the surface of the previous step. For this, let me fix some notation. So X will always be the surface we start with, and X prime will be the blow up of X in some points in each individual steps. And now, after having seen step 0, let's go to step 1. And maybe I should remark here, this is not only a weak Del Pezzo surface, but even a strong or normal honest Del Pezzo surface, since there are only -1 curves occurring and no -2 curves. Okay, step 1, we take our previous weak Del Pezzo surface to be the one we start with in this step. We already computed its automorphism scheme, the connected one, and we want to blow up 2 points, for example, P11, being the intersection of the exceptional locus with the strict transform of the line z equal to 0, and P21, this exceptional locus intersected with the strict transform of x equal to 0. So those 2 points I want to blow up are in the picture here, P11, and P21 is somewhere on this exceptional locus. I'm just giving a qualitative picture here. Okay, then by Bloorshaft's lemma, again, we can compute the connected component of the automorphism scheme as intersection of the connected stabilizer subgroup schemes. And for the first point, let us observe that P11 is the point of intersection of 2 -1 curves. I told you that -1 curves are rigid, so they are preserved by out x0, and therefore their point of intersection has to be fixed. Therefore, the stabilizer of this point of intersection is our whole group. So this first stabilizer is out x0. For the second stabilizer, it's not so easy. For this, we have to observe that the points on our second exceptional locus, E2, 0, correspond one-to-one to tangent directions at the point we blew up in order to obtain this exceptional divisor. Tangent directions there correspond to lines through the blown up point, correspond to members of the pencil lambda x plus mu z. And since P21 was the intersection of our exceptional locus with the strict transform of x equal to 0, we want to preserve the line x equal to 0. And now we see where it goes under this matrix. So x goes to x plus cz. So the line x equal to 0 is preserved if c is equal to 0. So we get this automorphism scheme, c equal to 0. Okay, and again, I give you the configuration of -2 and -1 curves in this example. Now we have here the 2 exceptional divisors and one additional -2 curve, the strict transform of x equal to 0, which is there because we've blown up 2 times on this line, so it becomes a -1 curve. And for this example, let us observe that this is not a strong or honest del Pezzo surface anymore, since we have -2 curves in there. It is only a weak del Pezzo surface. Okay, and now let's go on to the next step of our example. As I told you, in each step, we start with the del Pezzo surface of the previous step. So we have this one, we already computed its connected automorphism scheme to be this, and we want to blow up 1 point. For example, P12 on the latest exceptional divisor E11, and P12 should be the intersection point with the strict transform of this conic. Then again, by Bloorshaft's lemma, the connected component of the automorphism group is the stabilizer of this one. And I won't give you the details of the calculation, but you can check that those matrices stabilize our point. As I told you, I won't give you the details, but if you want to check, you have to determine the action of out x0 on the latest exceptional divisor E11, and then it turns out that these are precisely the matrices fixing the point. And in this case, the configuration of -2 and -1 curves looks like this. And maybe as before in the above picture, I can draw in the point P12, which would be somewhere here. Okay. Of course, now you all know how the procedure works and what we do in the next step. Let's have a look at step 3. Start with this del Pezzo surface. We know its automorphisms already. We blow up, oops, that was too much. We blow up 1 point, say P13, on the latest exceptional divisor, which is the point of intersection with the strict transform of the same conic we used before. So this point would be located somewhere here. And then we compute again its connected automorphism scheme. I won't tell you the precise computation, but if you use a pencil of cubic curves to compute the action of out x0 on our latest exceptional divisor E12, one can see that our point P13 is fixed by out x0 if the characteristic is 2. And if the characteristic is not equal to 2, we need the condition that f has to be 0 for P13 to be preserved or fixed. And as always, I give you the configuration of curves in this case, which is the following. So now in this example, you've seen that we obtained two weak del Pezzo surfaces depending on the characteristic. And in the next step, we're only going to go on with the one in characteristic 2, because there we're going to encounter some interesting non-reducedness phenomenon. So only the one in characteristic 2 is the one we're using for the next step. We already computed its automorphisms, and we blow up one last time. So this will also be the last step of my example. We blow up a point P14 on our latest exceptional divisor, which is the intersection with the strict transform of the conic we always used. And it would be somewhere here. Then again, we can compute the connected component of its automorphism scheme, and it is this. And we see that it is non-reduced since we have the condition f squared equal to 0. I didn't prove that to you, but after having showed you the picture of the configurations, I will give you an intuitive explanation why non-reducedness phenomena occur here. And the configuration of -2 and -1 curves looks like this. I think it is clear from all the pictures we've seen before where all the curves come from, except maybe this curve. But if you count it, you may have noticed that we have blown up 5 times on this conic. So the strict transform of this conic to the 5 times blow up will be a -1 curve. So it has to occur in our picture here. Okay, and now since we haven't done this computation, I will give you the intuitive explanation for non-reducedness. So if you look at this conic, you can see that it is preserved by the matrices with the condition f squared equal to 0. Maybe I can add some tiny computation here. So xz under our matrix out x0 goes to e squared xz, because z goes to e squared z, and y squared goes to e squared y squared plus 2e f yz plus f squared z squared. Okay, and now you see if the characteristic is different from 2, the conic is preserved precisely if f is 0. And in characteristic 2, the conic is preserved if f squared is 0, because this term vanishes. So the condition in characteristic 2 is weaker, which leads to the non-reducedness phenomenon. And this also gives an explanation why non-reducedness phenomena only occur in small characteristics, because the curves that appear in the pencils, which we use to calculate the stabilizer subgroups, have only small degrees. So now
but the construction works for in any characteristic, just the automorphism group changed. Is it correct?
Yes, exactly. So the construction and Bloorshaft's lemma and how you blow up points is all the same, but as you see in this example, in characteristic different from 2, this point is preserved if f is 0, whereas in characteristic 2, this term vanishes, so we need the condition f squared to be 0 for our point P14 to be preserved.
All right.
Mm-hmm. Okay, and now I will stop with the example, although this is only a weak del Pezzo surface of degree 2, and we could still blow up one more time, but I think you all know how this works. Okay, let's now put this example into a bigger context. In this example, we blew up some specific sequence of points, but to obtain a classification, of course, you have to go through all combinations of possible points you can blow up, and such that the blow up is still a weak del Pezzo surface, so at most -2 curves can occur, and such that the global vector fields are non-trivial. And in order to get the idea of the complexity of these point combinations, I collected some other possible choices of blown up points, which we could have chosen originating from the same starting point as in our example. And this is the next slide. Maybe here I can show the full slide like this. Yes, so in this picture, you remember we started with this configuration of -1 curves in our example, and in all those other pictures, the thick lines are -2 curves, whereas the thin lines are -1 curves. I won't go into detail of this example, I just want to show you how complex those combinations are, and I want to tell you which is the path that we have taken in our example. So in the example, we have first blown up 2 points and ended up with this configuration. Then we blew up 1 additional point and got this configuration. Then we blew up 1 point more. And we even saw these 2 cases, but I only wanted to go on with the case in characteristic 2, as you remember. And then we blew up 1 point further, and we ended with this case. This is a weakday Pezzo of degree 2, and we could still blow up 1 more further, and there are those 2 possibilities. So what should be the quintessence of this slide is that what you have to do in order to handle this complexity of point combinations is that you have to find a good order in which to treat all those cases. But I don't want to go into details of this ordering issue. I rather want to show you the results of the classification. So let's now go to the classification. This is a list of all weakday Pezzo surfaces with global vector fields of degree greater or equal 5. I can tell you what the columns in the tables are. So here we have some naming of those surfaces, which we just chose for the paper, but maybe I can tell you the first sign there always tells you the degree of the respective weakday Pezzo surface. Then in the second column, we have the configuration of -2 and -1 curves. Again, -2 curves, thick lines, -1 curves, thin lines. Here we wrote the -2 curve configuration again, but you could already see it from the picture. We counted the number of -1 curves in here. You can already see it from the picture as well. Then we determined out x0, which is this column. Of course, this depends on the chosen realization of x as a blow-up of P2. And if you have the precise shape of out x0, you can check whether it is smooth by checking whether it is reduced or not, since that is equivalent for group schemes. And then we have in this column the moduli in which these families occur. We see that all these weakday Pezzo surfaces occur as singletons, but in smaller degrees, we will also see that there are one-dimensional families. And the last column is maybe the most interesting one. You see that in degree greater or equal 5, all weakday Pezzo surfaces with global vector fields occur in all characteristics. So there's no characteristic P stuff going on. And here in this small table, I just wrote down the 2 weakday Pezzo surfaces with global vector fields that are not blow-up of P2. So P1 times P1 and the second reciprocal surface. Okay, so you see in all characteristics these occur. Maybe now let's have a look at 1 degree smaller, where there are 5 cases that are really special to characteristic 2. Let's have a look at them. You see that here we have 2 D4 configurations of -2 curves. They have the same picture of -2 and -1 curves, but they have different connected automorphism schemes. We also see that a configuration of D4 -2 curves already occurs in characteristic different from 2. So these 2 cases only add 1 additional case in characteristic 2. Then the phenomenon with same configuration, different connected automorphism schemes, and already one of these configurations occurring in characteristic different from 2 is the same for D5. But now let's have a look at this special case A3. Here we have this configuration. We see this configuration already occurs in characteristic different from 2, but in characteristic different from 2, the connected automorphism scheme is reduced, whereas here it is non-reduced. Now let's have a look at the table for degree 3. Here we have again 2 E6 configurations in characteristic 3, 2 D5s, 2 E6 in characteristic 2. This is the same phenomenon as before, but now let's have a look at this special case, the A4 -2 curve configuration, because this case does not occur in characteristic 0. Here you see there's no A4 -2 curve configuration, but you have this one in characteristic 2. And you also see that the connected automorphism scheme is non-reduced and finite. And one can also observe from the classification that this group 1, 1i with I squared equal to 1 also acts on the other weakday Pezzo surface in other characteristics, but there it is discrete, and therefore its connected component of the identity is trivial. So there, this group does not show up in our list, only in characteristic 2, where it is connected. In degree 2, we encounter the same phenomena as we've already seen. We have some finite group schemes here and some nice pictures here. And maybe the last slide to end this talk is the most beautiful one of the weak-del Pezzo surfaces with global vector fields of degree 1, where we encounter all the phenomena we've seen so far, same configurations, but more cases, and non-reducedness, and also a lot of beautiful pictures. Thank you for your attention.
Thank you, Claudia. Let's thank Claudia. Okay, let's in Zoom and in with claps. Thank you very much. Thank you for a very nice talk. Yeah. So questions. Alexey Igorevich, do you have questions?
I thought I already gave a lot of questions.
It was a joke. Yeah. Okay. So. Okay. Claudia, I don't have questions since I know your work very well. Yeah. So it's okay. So Liana, do you have question? No. Okay. No. No.
Are you going to single everybody out?
No, I just ask everyone whose picture I see. Okay, there's a there's a question.
There's a question in the chat.
Yeah. Let me. Answer is yes. Yeah.
I don't know how to open the chat. Could you?
I'll read to you. From this list, can you obtain the list of connected components of automorphism group of Duval-Del Pezzo surfaces?
Sorry, how did the question start?
Can you get from your list the list of automorphism group connected component of Duval-Del Pezzo? Answer is yes.
Yes. So if you contract those -2 curve combinations, you get the RDP del Pezzo, since the weak del Pezzo is the minimal resolution of the Duval del Pezzo.
Two different views on the same problem.
And maybe one interesting point we can make here is that, for example, let's have a look at, well, take an easy degree, take degree 3. Here we have 2 D5 configurations in characteristic 2. And if we contract the configurations of -2 curves, we get 2 different rational double points of type D5. For this, you have to know that in characteristic 2, there are more than 1 D5 rational double point, because they're not taught anymore, so they're not uniquely determined by their diagram. And these 2 cases are precisely the 2 rational double points, D5-1 and D5-0.
Perfect. Yeah.
I think you can. I'm sorry. You cannot actually calculate the group schemes for the divided Pezzo surfaces. I think that's the problem. They might be different, right? I think that's the question. But you can determine the group schemes of the divided Pezzo surfaces from our list. So you might have more vector fields after you contract the -2 curves. It's not possible to get the list for the divided Pezzo surfaces.
In positive characteristic?
Yes, in characteristic at most 7. There's a problem.
I see.
And I think this is because, for example, if you consider the A1 singularity in characteristic 2, there are vector fields on the rational double point that do not lift to your resolution.
Okay. Good. Thank you.
Characteristic P phenomenon.
Any other questions? Okay. Thank you. If no other questions, let's thank Claudia again. Thank you, Claudia. Okay, like this. Thank you. Okay, and we're slowly going to the next talk by Olivier Benoit. And Olivier, are you here already?
Yes, I am here. Can you hear me?
Good. Yep, perfect. Yes. Good. So I think you can share your slides now.
So actually what I want to do, I'm connected twice with my computer and with my iPad, and I would like to share the screen of my iPad. There should be 2 Olivier Benoits connected.
Perfect. In the current
Yes, there are. It's okay.
So here I connected a,
Yeah, I see
my
the
iPad.
white screen. I see the white screen.
Okay, and so if I write on it,
Yeah, perfect.
okay,
Good, good, good.
so that should work.
Yeah, it works perfectly. Yeah. Ah, wait, I have to stop recording here. Oops.